Now in this video we're going to apply the baby residue theorem to a kind of a case study. We want to relate the coefficients of this function z over e to the z minus 1, which I'm going to write out its power series at 0 in this way, which I left out the powers. I want to relate the coefficients of this power series to these infinite sums here. And as I mentioned at the beginning of all of this, we're going to get some of these nice formulas, and we'll get a systematic way to compute all of these different types of sums. So to start with, we need a simple way to compute residues at simple poles. So if I have a function that's analytic, except it has a simple pole at w, which just means pole of order 1. And if I have a function that's analytic at w, well, I can compute the residue of f times g at w just by evaluating g times the residue of f. And here's the reason. So f has this simple pole. So around w, it's going to look like, I shouldn't write f of w. F of z near w is going to look like residue of f over z minus w, and it has a simple pole, so that's the only piece of the principal part, and so I'll have plus analytic stuff, so stuff that's analytic near w, and when I do f times g, what's going to happen? Well, maybe it helps to write out g near w naught. Well, I'm going to have g near w. I'll have g of w, and then I'll have a plus higher order terms. So it'll be like g prime of w, z minus w, and so on, higher order terms. But when I multiply this out, I'm only going to get the 1 over z minus w term by multiplying g of w times the residue here. So I get this plus analytic stuff. What's the reason for that? Well, these higher order terms times this simple pole will give me something analytic, and that won't influence computing the residue. So again, the residue of this product now will be this coefficient, which is just the value of g times the residue of f. Now let's start to dig into the example that we're studying. So we'll say f is this function, which this function is analytic at 0 because the 0 in the bottom at 0 gets canceled by the z on the top. But this function is meromorphic on all of C because it only has poles at 2 pi I times an integer, take away the origin, again, because we've kind of canceled out the pole at the origin. But so why are the poles simple at these points? Well, I can compute a power series expansion for the denominator by taking the derivative at its zeros. So the derivative of e to the z minus 1 will just give me e to the z, and then I plug in 2 pi I n. So I'm just plugging 2 pi I n into e, which gives me 1. So the power series at this point will start out with z minus 2 pi I n, and then higher order stuff. So I'll have 1 plus something that's analytic and vanishing at 2 pi in. I don't really care about this piece, but I do need to know that it vanishes at the point in question. And so now I can write out this function as z over z minus 2 pi in, 1 over 1 plus g, and using the previous formula, I can compute the residue at 2 pi in. Well, I can stare at this part. This part clearly has a simple pole with residue 1, and so I just need to know the value of this part at 2 pi in. And so I'm plugging 2 pi in into z, and this part, g at the point in question was 0. So I just get the residue at 2 pi in is 2 pi in. So that's easy enough. Okay, let's push this a little farther. We can use residues to actually compute the power series coefficients as follows. So again, we're going to write our function f in a power series, and it's just sort of customary to write it as bn over n factorial because the bn's are called the Bernoulli numbers. And this is just near 0 again because the function f has poles at various places. So this won't converge everywhere. It'll stop converging once you hit a pole. Nevertheless, we can still use residues to compute the coefficients. The residue of f times z to the negative n plus 1, so the residue of that at 0, will just give me the coefficient that I'm interested in. And this is just another way of writing the formula. That the integral of f against w to the negative n plus 1 will give me the coefficient of z to the n in f's power series at 0. This should be for r small. So we don't want to get close to any of the poles for this to be true. Okay, and I can also compute the residues at the other poles of f. How can I do that? Well, I'll just use my trick again. So here was how I was computing simple residues. Let's see, f here still has simple poles at all of these 2 pi ik's. And z to the negative n plus 1 doesn't have a pole at these points, so it fits into the category of this. So now I would just need to have the value of this piece at the residue. So I would have 2 pi ik to the minus n plus 1 times the residue of f at the point in question, which we already said that this was 2 pi ik. And so you get, there was an n plus 1 here, so you get 1 over 2 pi ik to the n. Okay, now we've computed all of these residues. Let's assemble them and get some interesting formulas. Okay, now we're actually going to apply the residue theorem. So consider this integral of our function f, and again, here's f. And I'm going to integrate along this circle here to avoid poles. because the poles only occur again at 2 pi I z take away 0. So if I'm at an odd multiple of pi, I'm not going to hit any of the poles. Okay, and this looks like a formula used to compute a coefficient of an analytic function, but f is not analytic inside this circle. It's meromorphic there, and that's what the residue theorem does. It sort of accounts for the lack of analyticity inside there. So this will be equal to the sum of the residues, which luckily we've already computed. So the residue theorem says you have to look at all of the different poles and compute the residues. So we have a pole at 0 because of this term, and the residue at 0 was the coefficient that we're after. And we're doing this at 2n here, and I'll explain why in a second. But now I'm going to go around to all of the other poles, which are 2 pi I k, and I compute these values. But since I'm doing this at k and minus k, I might as well sum over just the positive k's and multiply by 2. So that's why I have the 2 here, and that's also why I only want to do this at 2n, because if I did it at an odd number plus 1, I would get contributions that just canceled out, and we'd actually see that the odd Bernoulli coefficients were 0, at least past a few coefficients. I don't want to get into that too much. Just trust me that you were mostly interested in these even coefficients. But what have we gotten out of this? We have these coefficients that may be of interest or we can compute somehow, and these sums. And these are kind of interesting sums because except for this 2 pi I here, they do look like the infinite sums that I claimed we were after finding formulas for. But now we can basically compare them by estimating star up here. So star, this integral, I'm going to estimate it basically with Cauchy estimates, except f is not analytic inside the circle, but I can still estimate the integral in the same way. So I'll get the supremum of f on that circle times the radius to the power involved, minus 2n, and I do have to keep my capital and lowercase n straight here. Okay, and then we had a homework exercise to show that the denominator in f is bounded below. And so that gives us a bound on f. And if the denominator is bounded below, then I get a bound of the form a constant times w, and in this case, w is equal to these odd multiples of pi. And so you get out of this a bound constant times odd multiple of pi to the 2n minus 1. And here we do want n greater than or equal to 1. And if I send capital N to infinity, this goes to 0. So that gives me a comparison between these numbers and this, but I'm sending capital N to infinity to get an infinite sum. Okay, and then I'll spare you some of the details, but this directly shows us that I can get a formula for these sums of k to the 1 over k to the 2n, where k goes from 1 to infinity. So you can actually solve for it and get these formulas. And maybe it's better to try to find it yourself. And at one point, we actually found some of these coefficients by hand by just doing the division of the power series here. So the first coefficient, b2 over 2, is 1/12, and b4 over 4 factorial was this number. And again, it's better to work this out yourself, but you can put these in here and get these kind of famous formulas. So this number here will give you pi squared over 6, which gives you the sum of 1 over the squares. And you can do the same thing with 4 to get pi to the 4th over 90 gives you the sum of 1 over k to the 4ths. And if you computed b6, you could get a formula for 1 over k to the 6th. And that's a good exercise to try to do that. And you see exactly that these sums directly depend on these Bernoulli coefficients.